Welcome to Big Bucks Physics, where we make the big bucks and you make the big grades. Today we're going to be learning about inclined planes. So if you choose to zoom to like minute 10 of this video and you get a crappy grade, that's not our problem. We are not liable for that. Alright, so we're going to jump into the conceptual part of inclined planes. Basically, what's happening is an object is sliding down a hill. That's it. I don't know what the problem is there, but that's all it is. So I'm pretty sure we'd all agree that the object would slide this way instead of sliding up the hill, so it would slide down the hill because gravity acts downward. So we're gonna draw out a problem and get this thing started. Okay, so when looking at these inclined plane problems, it's all about the perspective and the direction in which the forces are acting. So for starters, the way we look at it, we might want to tilt our heads like so. And now you can see that the object with mass m is flat, and we can draw out our axes, the x-axis and the y-axis, as you can see in the model. So now we're gonna turn the camera back. Alright, hot dog. So now we have these axes at a weird angle. But we still know that the force of gravity is acting down on the object, just directly down, just going straight down. The axes extend, as you can see. The y-axis extends here, and then the x-axis is parallel right here. So we can see our triangle, hopefully, right there. The angle of the triangle would be equivalent to the angle of the inclined plane, which is theta in this case. So we're going to draw our theta here. Using our laws of sines, cosines, and tangent, or the trig functions, we can solve for FGY, FG, and FGX, because we already know FG, which is mass times gravity. So the movement of the object is going along the x-axis, which is parallel to FGX seen here. So basically the force in this equation would be FGX. So looking over here, we have our equation force equals mass times acceleration, and then we set the force equal to FGX equals mass times acceleration, and once we expand it, we can go back to the triangle and see that the FGX is opposite from the angle, so you would plug in sine theta times mass times gravity equals mass times acceleration.
So this is our first inclined plane problem. You have a mass of 10 kilograms here, and then it's sitting on an inclined plane which is angled at 35 degrees. And pretty much you know the box is going to go down, so that's going to be your mg sine theta. And then here you have mass of mg, pretty much gravity pulling down. Here you have sine of theta, which is 35 degrees, and then my cosine theta of how it's pulling down. So then first you're going to use the equation FMA, which is force equals mass times acceleration. And then what you're going to do is pretty much substitute in your variables, which is mg sine there, and then ma stays the same. So you're going to get rid of the m's, pretty much cross them out. Rearrange it to have acceleration all by itself, which is then it's equal to g sine theta with sine 35, which theta is at this point. Then pretty much you just plug in your variables. Gravity is negative 9.8 because it's going down, meters per second squared, and then sine of 35 is 0.57, and then you get your acceleration to equal negative 5.58 meters per second squared.
Okay, so now we're going to put a little real-life application in this, and we're going to say a car, which is the circle right here, in San Francisco had faulty brakes and is now rolling down a hill at like a 4-year-old or something, I don't know. So the incline of the hill is set at 22 degrees approximately. So with that information, we're able to place the 22-degree angle here as well, using basic knowledge of inclined planes. And once we complete our triangle with mg cosine theta and mg sine theta, we're able to jump straight into the problem. So we're trying to find the acceleration of the car down the hill. So what we're going to do is we're going to plug in mg sine theta into force, and we're going to set it equal to mass times acceleration. So our masses cancel right here, and we plug in g sine 22 equals acceleration, and once we simplify that, it's going to come out to negative 3.67 meters per second squared. This is our real-life application of San Francisco faulty brake problem. Initiate, rolling, 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 rolling. Roll! This is the inclined plane problem in San Francisco with an applied force, which in this case is 5 trying to stop the car from rolling down the hill and hitting that 4-year-old, which is the chair, for lack of better whatever. Let's just get this going. Initiate. Oh, see? Now we're rolling slower. We're rolling slower this time. Yeah. Hit that chair soon. It's coming. Oh, there she is. Got it. Yep. Got it.
This is the incline plane problem with force applied. So you have your truck, which is represented by this box here. It has a mass of 5,000 newtons. You have 2 forces acting on it, which is FGX, gravity pulling it down, and force applied, trying to slow down the acceleration of the truck. We use the equation FMA, which is force equals mass times acceleration, to solve this. And then, so you're going to take your FGX, which is gravity, and then sum your forces with force applied equals mass times acceleration. And then you're going to take your mass of your truck, which is 5,000, and then take 5,000, and then sine of 22 plus 500 newtons, which is the force applied, equals 5,000 times acceleration. You plug that into your calculator, sum your forces here, and then you still have your 5,000 on the acceleration. After summing your forces, you get this number, and you divide 5,000 by each one, and your answer is negative 3.57 meters per second squared.